Okay, thank you, everyone. Good morning again. So day two, we sort of, walked through an overview of what the PAWR test beds were, and I tried to sort of just briefly introduce the kind of research topics that this digital infrastructure enables. So today, I just want to do a much more deeper dive as to how you, an experimenter, or if you're a test bed operator, can leverage some of the tools, some of the kind of research APIs, toolkits we've developed, some sample experimentation. So again, look at it through whichever lens you'd like, either as an experimenter, a user, or a test bed operator. In terms of flow, I'll start with Coliseum, which is sort of the emulation environment. I feel that's sort of a little bit easier because it's a little bit more contained. It's a remotely accessible test environment. And then everything you see on Coliseum, I'll try to connect to how you can export that to PAWR test beds, or actually bring that back into your host institution if you do manage a lab set up locally. So yesterday, I forgot to sort of do justice to the collaborators that work on PAWR and on the Coliseum infrastructure. So this is the team at Northeastern University. And then, also wanted to emphasize on this slide is that, anybody who here runs a test bed sort of understands that it is not just, one person who's standing up here and speaking. There's an entire team behind. So there's a whole host of students, PhDs, postdocs. The one thing I do want to emphasize is the DevOps team. So the kind of infrastructure we run, we have a dedicated core team of professional staff that basically runs eyes and ears, has a finger on the pulse on how the infrastructure is doing, what sort of an uptime do we have, keeping up to date with all the security, the patches, et cetera, et cetera. So just want to make sure that they feel, that they're credited, and others who do the same kind of a job profile in this room also feel acknowledged. So PAWR, again, just, if you weren't here yesterday, I really just 30 seconds, a quick overview. So this is an initiative founded at the National Science Foundation since 2017 as a public-private partnership developing test beds across the country. And the idea here was to coalesce, the investments that the NSF makes into individual institution test beds and actually instead make large-scale investments. So again, $100 million program. We're sort of in year 5 of this program with 4 platforms. So just quick recap: PAWR out in Utah, Cosmos in New York City, AirPower down in Raleigh, North Carolina, and ARA, which is out in Iowa State. And again, the idea here is to have multiple stakeholders represented that can leverage, use, and collaborate and cross-pollinate ideas from fundamental research to applied research to proof of concepts. Okay, I'll jump into Coliseum. So Coliseum, again, it's a large-scale wireless systems test bed. Again, by the numbers, it is the world's largest channel and network emulator. Is able to emulate 256 by 256 100 megahertz RF channels. So again, 65535 cross connection, so very, very large in scale, has a heterogeneity of computing resources, CPUs, GPUs, FPGAs. So as a programmer, you have the ability to leverage any mode of compute that you may want for processing purposes. And you'll see how this sort of plays out. Again, completely remotely accessible, access control, resource management, scheduling, all of that sort of comes in, and then supports some of these areas. And I'll get into each one of them in more detail. The key thing to realize is it's not, like NS3 or a simulator, even though those tools have value in the experimental life cycle, but this actually has RF hardware in the loop. So it's real-time emulation with wireless signals and emulated channels, and it combines in a single instrument the flexibility of virtualization. So all of this is running in a softwareized, virtualized radio access network environment and a compute environment supported by LXC containers, fidelity of the hardware, and the scale of a simulator. So significant investment by the US federal agencies, DARPA, which is a defense agency, the National Science Foundation, and then, university contribution. So all in, we're in for about, $35 million into just setting this single instrument up. So from the time of putting it all together to actually keeping it in operation over the past 2.5 years. So 128 software-defined radios co-located with x86 servers. And then if you see those blue cables, those are coax cables. And I'll talk in more detail on how the channel or how the RF signal propagates from a transmitter back over to the receiver. But the idea here is that you have the ability to do large-scale experimentation. And then on the right is a representation of what's called a scenario, which is essentially a virtual world made by programming the filter taps on the channel emulation system, by modeling multiple modalities from Doppler, frequency shifting, phase shifting, et cetera. And you're able to model different positions, mobility, as well as aerial UAVs that can be modeled in this particular environment. That's the architecture. It's a busy slide, but in reality, what I'd want you to take away is it comes with a nice wrapper of a resource management system with multiple network elements that allow you complete isolation if you're an experimenter. So you have access to the internet, you have access on a management scale, and then you have access to the emulation system. Now, there are 3 or 4 different networks that I just want you to keep track of. Starting on the radio side, it's the competitor access network or a user. So a user such as yourself will have direct access to the standard radio nodes, which is just a combination of an x86 server with a SDR. You also have the traffic generation system. This is sort of the IP level traffic that you will generate. You have the scenarios, which is how you'll program the channel emulation filter taps to make what sort of wireless channel measurements that you'd want to make. And then you also have the ability to bring in hardware in the loop. So you can actually connect radios for which we don't have a software-defined profile. So we've been working with lots of COTS radios. We've been working with Zigbee, IoT kind of radios, as well as certain radios where the waveforms are a little bit more proprietary. So think more like military applications. So again, this is something that's quite important, which is in terms of what you're able to do, you're able to emulate it in real time and in a very deterministic fashion with very high fidelity. And you have the ability to sort of develop complex RF scenarios, meaning you're able to model how a particular node in a dense environment, a rural environment, or out in a tactical environment sort of behaves. This is sort of the MChem. So this is where I'll spend a minute or two just trying to explain. So what you see on the left is this notion of what we call a standard radio node, which is a combination, as I said, of a Dell R730 and an USRP X310. Now, once you sort of load, and I'll talk about how an experiment is executed on Coliseum, but pretend for a second that you have a transmitter node. Let's see. Yeah. So if you have this as your transmitter node and you're able to sort of make a waveform, a 4G network, a Wi-Fi network, you actually send that out in the analog domain over to the channel emulation system. On the channel emulation system, you have a sister, kind of a paired USRP X310 that receives it in the analog domain, transfers it into the digital domain, and sends it into this very, very high resolution FPGA, which is a Vertex National Instruments FPGA built by Xilinx. And here you sort of do the programming of the filter tabs. So as I said, these are 512 filter tabs that are there. However, we only program 4. Now, why we do this? It's just because of mathematical complexity and the ability to manage the amount of data it takes to generate a scenario. So on average, a scenario can be anywhere between 4 terabytes all the way up to 15 terabytes, and all of that needs to be programmed on the emulation system before you can run an experiment. So we've done certain tricks, but here's a number. So 4 non-zero filter taps, and again, I'll talk about the math a little bit, but then that's where you sort of do the manipulation of the signal in a digital domain. You spit that back out. So pretend for a second, this is your receiver. You spit that back out from the channel emulation system back into the USRP, and then that goes out in the analog RF domain, back into the receiver USRP, and that's where it's again post-processed. So that's sort of the life cycle of how a transmitter or a receiver will connect signals between the Coliseum infrastructure. And this is where the brains of it all are, and it's all controlled by what we call the scenario server, which is what essentially just programs the filter tap values for Coliseum. So the RF scenarios is where the entire game is. And what these RF scenarios and then the traffic scenarios on top are purely deterministic. So the experiments with the same scenario should execute in the same way. And this is where the whole notion of reproducibility and repeatability comes in. And then we have the ability to have, stochastic distributions in the filter taps. And this is sort of, a kind of a notional picture of how, the performance drop is going to happen if you are trying to have some kind of a varied distribution, or you're trying to keep only certain desired channel effects. So the idea here, again, the operative term is it's an easy comparison between algorithms. And this is something that's a very, very powerful tool that's been leveraged by a whole host of US universities and international partners. This is, again, just a cartoon picture of what a scenario looks like. So scenario in real terms is something where you have a representation. So this is a scenario we call Alleys of Austin. So this is Austin, Texas, down in the south of the US. We've been able to sort of build through sophisticated, and I'll also talk about how we do the data collection. So we do it in a few different variety of ways. This is a very high fidelity scenario, meaning that we went and actually did ray tracing, captured all of the terrain information, and then sort of created a tactical scenario where you actually had a platoon that had to descend on a major US city that has 5 different squads, and each squad has 9 members and also has a UAV. So there's fixed infrastructure, there's mobility built into it, there are sensors, there are cameras, there's UAVs, and all of this is run for a total of 1,000 seconds. And there's a video here if you're curious to see, but this sort of maps a 1 kilometer by 1 kilometer square area and has a very, very rich fidelity. So now, if you're trying to do any kind of algorithmic development work or trying to evaluate either a 4G, 5G network performance in this kind of an environment, you now have something where you have a very rich system. Now, pretend for a second you wanted to do this on Powder, on AirPow, on Cosmos. This requires extreme levels of coordination with the actual hardware provider. You'll need multiple people on the ground. So the idea here is that you best be sure that this experiment is actually going to work at some level before you actually go and spend the cycles doing this out in the wild. These are more sort of scenarios we've developed. Some of these, and the fidelity of these is a little bit different. So these were collected. The one in the Boston Public Garden was collected over a tool called Wireless Insight that's developed by a company called Remcom. And there we collected some data, but mostly we just did some synthetic injection or some interpolation so that we could program the filter tap. So is this the most realistic channel model of Boston? Probably not, but gives us enough fidelity that we can model what's going to happen in a downtown urban area such as Boston. Then this one is more interesting, which is, this is the powder test bed out in Salt Lake City, Utah. So I talked about it. This is their the campus deployment. So this is where the university is. These are all the real locations where actual SDRs are mounted on rooftops, as well as some on streetlight furniture. So we went out and we collected large amounts of IQ samples from each of these different locations. And then we sort of combined that into the scenario creation algorithm, and then also collected the terrain information from Utah. So now we have a virtual world of Powder. And what I did on the said on the last slide, if you wanted to conduct an experimentation, either around scheduling or around performance or around monitoring, you now can actually do that in Coliseum with high reliability, that the way it's going to work in Coliseum, you have some notion of how this experiment would work if you were to take it out into the wild. So again, it's a stepping stone, it's a risk mitigation tactic, but also allows you a very cool, repeatable, reproducible tool. And what kind of things you can do, you'll see very shortly. So this, again, if you remember from yesterday, I'd sort of talked about this journey of a container. On Coliseum, you run what's called a LXC, or a Linux container. And that's where, that's something that you as an experimenter are going to start with. We provide a whole bunch of reference containers. I advise you to go to the Coliseum.net website and see what all we advertise. And that's your basis of starting. From there, you can sort of make certain modifications. And then, as I said, you can iterate over Coliseum if you want to work on Powder eventually. you're able to take that container, spread it across multiple transmitter receive nodes, and then you're able to validate that either in your lab environment, or you can take it all the way up to the large scale test platforms that we have at PAWR Cosmos and at AirPow down in Raleigh. So this is sort of, and again, this is where this could be your home institution. This could be another test bed here in Europe, in Greece, in France, in Spain. And the idea being that the lowest common denominator is as long as you support virtualization and you can host our containers with some glue code, again, that's the caveat, we should be able to have some nice cross-pollination of ideas. So let me get into more of the use cases. So I'll pause here. I know it's a long session, so just want to keep it interactive. If there are any questions, just please draw my attention. Happy to answer those as I go along. But if not, then I'll just switch over to some of the use cases applications so you can actually tie in the infrastructure that you've seen as to how we sort of exploit that for certain research areas. So again, yeah, just before we get there, we do serve diverse communities. So we are serving the academic community, the US Department of Defense, industry partners, and again, we provide access and support through the funding that's provided to us by the US federal agencies. So OAI is something that you've learned about, you've heard over the past day and a half. OAI 5GNR, sort of the headline here is, it works on Coliseum, works right out of the box. We put significant amounts of effort working with the OAI dev team at Eurocom and at the Alliance. And basically we have a working end-to-end version of instantiating an OAI soft UE, an OAI G node B, as well as the OAI core node, and sort of seamlessly making it work over the massive channel emulation system. So if you're just getting started, which I doubt most of you in this room are, but if you wanted to just, play around with the OAI software stack and whatever you've heard over the past day and a half, wanted to instantiate that, you're most welcome to do that. So this is what the base containers, which I had talked about earlier. So this is just an LXC container, as you see, completely self-contained, brings up the interface, connects it to the USRP, compiles your code for you. Same thing on the G node B side, and then same thing on the core network. And again, as I said, credit to the Eurocom team for helping kind of support this. And each of these experiments that I'm bringing up here has an associated demonstration video. If you don't find it on our website, please do, let me know. So that was a single UE. We have been able to work with multi-UE setups. This is still a work in progress with within the OAI dev team. Doing it in an over-the-air environment, and any of you can attest, is quite challenging given the diversity of channel conditions. Given that we are able to do this in an emulation system, we can actually very nicely control what sort of channel propagations we have. And to help us debug, we can always turn the path loss all the way down to 0, and sort of, do this at a level that's beyond what the UE simulator or the RF sim or 5sim mode, if you're familiar with the OAI stack, allows you to do. So happy to report, even though I showed 2 UEs, we're able to support up to 6 right now, working on some stability performance issues. But the idea here is that you have now, for the first time, an end-to-end 5G standalone architecture based on OAI that supports multiple UEs, and you're able to instantiate that on Coliseum. Shift topics into ORAN. So we've been hearing, and we heard a bunch from Naveed over the past hour around, the RIC, around deploying experiments on ORAN. So again, happy to report, sort of support this particular architecture on the Coliseum environment. So right now, it works with the SRS LTE stack, which is the 4G version of SRS. On the OAI side, there was a very recent release that now for the first time implemented the F1 split between the CU and DU, and now is working towards working with commercial radio unit vendors, as you heard from Raymond, or you will hear later today, on supporting the option 7.2x ORAN split. So we do today have a 4G version of this architecture working on Coliseum. Again, all containers are available. You can download them locally, play around with them, or instantiate them on Coliseum if you wish to, and then sort of conduct some of these experiments. And I'm going to talk about a few coming up. So I may have mentioned this, but this is sort of our foray over the past 6-8 months into supporting ORAN and Open RAN experimentation on Coliseum. So this ties in nicely with what Naveed talked about, and this is what we are calling Open RAN Gym. What this is, or what the main motivation here is, to develop an open source toolbox for XApp development and Open RAN experimentation, supported primarily on Coliseum. So what does it enable? It enables data collection, enables AI ML model design, training, testing, deployment of the near real-time RIC, and runtime inference control on a software radio access network. So that's a mouthful, but what does that actually mean? So on your right side is where we have the ORAN kind of an architecture with multiple DUs, CUs, RUs, the near real-time RIC. Primarily what we support is the OSC, the ORAN software community contributed ORAN RIC. Probably want to get in touch with Naveed to sort of talk about supporting FlexRIC as well, but we don't at this present time. Then what's more important here is you have this beautiful life cycle with a nice feedback loop, and all done in an automated way. So once you actually understand this pipeline, you're able to develop it, you now can just iterate on it very nicely at a click of a button. So all the way from data collection, model design, training, testing, deployment, rinse and repeat until you're able to optimize for whatever you're trying to do. So more details on how the architecture is set up. So right side is where the Coliseum environment is. Right now, we work with Coliseum, but I can also show you the pathway on bringing it into your platforms or to the PAWR platforms that are out at those 4 different locations. But what we have end to end is the following, right? So start from the right side, these publicly accessible experimental platforms, the programmable protocol stack. So as I said, right now it's based on the 4G SRS RAN stack, and that's the softwareized RAN. Then we have this API based system that's called Scope, which allows us to do data collection and control. So this is something where you're able to do not only data collection, but also the development of models and do some inference and training, both offline and online. And then this is sort of the main key piece, which is the ORAN compliant near real-time RIC, and the ability to have this XApp SDK that we have released. So this runs on an ORAN, a Docker cluster. We heard from Naveed about all the importance of all the different E2 terminations. We provide that for SRS right now, and we're very close to doing it on OAI. I know Naveed's done it on FlexRIC, but we're working on our own version. So what does that have? The RAN E2 termination on the connected back to the softwareized RAN, the E2 interface that's compliant, the E2 termination, the management, the routing, the database, which allows you to concurrently and online be able to query and write, and then these different XApps. Now, the beauty here is if you are not a traditional comms person, you can write the XApp without actually having clear understanding of what is going on the RAN stack, because you're going to just leverage what the E2 interface does, what the E2 service model provides you, and what the E2 AP allows you to do. And then all of this you're able to deploy in almost an instantaneous fashion on Coliseum, and then move it over into the PAWR testbeds. So this one is a little bit of a deeper dive on what we have done. Now, this is the demo that we showed at Mobile World Congress Americas last year. And what this was is running on Coliseum, the SDR, so that's what's doing the RF, the CU-DU split with the RAN E2 termination, and this is all in a container. So again, as I said, I want to stress this as much as I can. Hopefully this has an impact on you as you get started in this field, or even if you are deep into doing research into ORAN, this can be a tool that you can leverage. Instantiate very quickly, easily the XApp. We have multiple sort of XApps that we have developed that we publish, advertise. And then on top of all of this, we have this large scale service management and orchestration platform. So we have our XApp catalog, which is where we publish all the different XApps we develop. All of these are running on top of an LXC container. And then co-located with that for the data collection and training purposes, we have a machine learning cluster. So we have these large scale NVIDIA DGX A100. So these are all very, very sophisticated GPUs, which is what you can connect in online fashion for conducting your offline training. So you have Supermicro server, multiple NVIDIAs, and we're actually augmenting and enhancing this cluster if you wanted to leverage this. And obviously, we provide a large amount of data storage to keep your terabytes and terabytes worth of data sets if you wish to. So what's happening here, just to quickly run through, is the OSC near real-time rig, the XApps that are running for network control and performance optimization, and then connecting it all into a software RAN through the ORAN-E2 interface. So this was scope. This is basically what I talked about. This is the data collection model. Down there are multiple scenarios that we advertise. And now a little bit humor, and this is humor of an engineer. But basically, on your left, you see a Colosseum that is the real Colosseum down in Rome, Italy. A scenario of Colosseum on Colosseum. So that'll be the only joke you hear today. So basically, we've been able to sort of model using the wireless insight tools, a large number, so 10 fixed locations around the Colosseum infrastructure out in Rome, and then model it back on the Colosseum emulation environment. Boston I'd already shown. I think that's Salt Lake City on the right. It's a little bit hidden, but the idea here is that you can now, in these various scenarios, using this scope framework, collect the amount of data and the types of data that you would want. So you have these exemplary scenarios that are represented and are annotated to do data collection on your behalf using the framework that's available. And if you want more details, there are a bunch of papers that have been published, one referenced up here to the right. So this is the XApp development workflow. Again, happy to spend a little bit of time here, but this is best done if you tried it yourself. But the idea, just real quick, similar to what I had talked about here, is you start the near real-time rig, you start the base station, you subscribe to the radio intelligent controller, you start the XApp with the base station in a control loop, and then you basically have data flowing end to end, and you're able to do your AI-based design. Simple enough, right? But it is a little bit hard once you actually have to put all the pieces together and leverage, this entire infrastructure end to end. So really, credit goes to the team for providing this as a resource. And this is where also it's important to realize that you as a programmer, if you're a low-level FPGA programmer, you can basically, you have total control on that the USRP. You also have an FPGA on the x86 server that you can program if you're trying to do something more funky, like near real-time control on LDPC or any hardware acceleration that you want to deploy in an FPGA. You also have, obviously, the CPU cycles, whatever you want to do with that. And then, as I talked about, having a co-located GPU. So we actually have an older version of a NVIDIA Tesla GPU that is sitting right next to the X310. So if you wanted to do some, implement different compute architectures on NVIDIA, you have the ability to do that here. Or if you wanted to just use that for training and inference purposes, you actually can run that stuff here. So yeah, so this is basically the simple steps. Start your rig, connect it to the base station, deploy your XApp, and then you have the ability to have data flow go back and forth over there. And this is sort of what we are hoping that could be used and leveraged by experimenters. So the XApp structure, again, right, this is, I'm not sure, how much into detail, Naveed, you went in there, but this is sort of how, the XApps are being designed. And what's important here is, you can build your data-driven logic unit on the right side. So this is where the AI techniques of either inference, prediction, control, those are your models. Those are connected using the KPMs that the RAN exposes. And this is sort of what in 3GPP speak would be where the ASN1 encoding decoding happens. Sitting on top of this is the shared data layer. So these are all the different APIs that are exposed. So either you want to do database queries to the Redis database, you want to do query RAN KPMs using the RIG, or provide control messages from the RIG back and forth to the XApp. So this is sort of how it's set up if you want to develop your XApp. This again, I've talked about this in detail. The idea here is you prototype, you validate, and then you test, and then you iterate over again with these containers sort of migrating and moving from one testbed environment to the next. So this is on PAWR, meaning that we are able to transfer the containers. So these are the LXC containers with the softwareized implementations. And just to give you a sense, this is the amount of time it takes to move from Coliseum to the different test beds. Now, Arena is a local test bed, indoor over-the-air test bed, similar to the ones you have here at NITOS, or if you know about Orbit, very similar in spirit, antennas hanging from the rooftops, 32 of those. So that's literally about 6 miles or about 10 kilometers from where the Coliseum infrastructure lives to our indoor environment. Cosmos is out in New York City, Powder's out in Utah, using simply just a dumb data transfer of the container. Takes us about a minute and a half. This one is more because this one has the entire RAN stack, has the rig, and takes about 5-10 minutes to deploy. So what I want you to take away is, this is on the order of minutes to transfer the containers that you built in one environment and port it over to the next one. Then starting things is obviously takes a while to sort of ramp things up because everything needs to be compiled from scratch. And especially it takes much longer, in the order of half an hour to an hour if you're actually modifying the entire rig code base. But again, hopefully you appreciate the complexity involved and the idea that this is able to be done completely at a touch of a button. So you're not sitting in front of screen while this is happening. It just happens in the background, gets executed, and a report out comes back to you. So these are sort of some, kind of slicing based experimentations that we have done. So this is dynamic slice allocation. Again, this is just showing you 2 different slices operating, working in multiple different environments on Coliseum, Arena, Powder, and Cosmos. If you're an astute, sort of a keen observer, you start to notice what's happening in terms of, the channel propagation, how sort of the slice isolation happens. It's obviously not as seamless. There is quite a bit of noise, but in reality, you still have the ability to orchestrate how the slices are deployed and how you do assignments of the resource blocks to each of the slices. And again, each environment has a little bit of variation in how it executes it, but the results are very, very different across these heterogeneous environments. So, and these are like sort of different techniques, right? So here you have, first you have more resources allocated to slice A, then you have equal, then you have more resources allocated to slice B, and then you have a different environment that's, or a different deployment scenario that's happening here. But the idea here is that you developed something on one test bed and you were able to test it on multiple ones. That's sort of the main takeaway here. Couple more examples here. Just gonna do a quick time check. Okay, we're working on. So yeah, these are sort of more different XApp environments. Same Coliseum, Coliseum, Arena, Powder, Cosmos. The idea being developed one place, deployed multiple places, and you're able to do a nice comparative result comparison for this work. Okay, so that was all about ORAN, but Coliseum is also much more than that. So it is, we talked about the network level work, now getting a little bit more into the physical layer. We are able to support beamforming and massive MIMO on Coliseum. Any of you who has worked, so obviously, maybe quickly to go through why do we even care about massive MIMO, right? So massive MIMO is around spatial diversity, increased SNR, anti-jamming techniques, large number of antennas that you could sort of collectively use for spatial multiplexing. Challenges are coordinating and synchronization the transmission from different antennas. So timing becomes and synchronization become very, very important. And channel estimation, again, for, the mathematicians in the room, you understand estimating the channel or compiling channel matrices is quite a labor-intensive task. So what we found out was obviously we didn't have large-scale experimental setups for massive MIMO base stations. I don't know how many of you have access to those, but that's quite challenging to get. So this is, this is what we do. We have multiple standard radio nodes. So again, remember, each radio node is a x86 server and a USRP X310. So we essentially have connected, and I'll show you quickly, I'll scan that, put that up and come back to this slide. So this is what we've done. So we have an entire clock management system with octa clocks and grandfather master clocks where we're able to control the timing and synchronization across multiple different standard radio nodes with a master clock distributor, and you're able to sort of control timing in a very precise fashion, so you can collect all these X310 radios and then combine them into antenna arrays. So this slide says that we only have one Coliseum quadrant, which is 32 radio nodes outfitted with this infrastructure. Sort of happy to report we've been able to do that with 2 quadrants. So right now you can actually have a 64 radio node cluster that you can use for massive MIMO experimentations. And again, we support this. We sort of provide all the reference architecture. We provide the drivers required for this, whatever is required on these ZS SDR. So that's all provided. And the container is actually available. Again, I should have done a better job at updating the slide. So this is ready to go. So this is available for you to conduct experimentation. Now, Coliseum was primarily built for spectrum sharing purposes. So the idea here was that if you have the same spectrum, how do we smartly share, or how can we, in the time and frequency domain, how do we assign multiple physical resource blocks across different users or across different technologies, be it Wi-Fi and LTE, coexistence studies, or even some incumbent radios. Now, in the US, there is a framework called CBRS, Citizens Broadband Radio Service, which allows you in the 3.5 to 3.7 gigahertz spectrum to have the ability to share spectrum with an incumbent user. So this is why this particular topic area became very, very important, at least in the US, around spectrum sharing. And again, Coliseum just inherently is built to support that. So again, same kind of notion. You're able to generate heterogeneous traffic scenarios on Coliseum. You develop your algorithm, you do a design, you do a closed loop refinement, and again, ready to deploy and iterate on Coliseum. AI and Internet of Things. So again, the main thing you're going to see is this notion of a closed loop feedback system, which is a very, very powerful tool, especially when you're in early days of conducting experimentation, either as a student, an industry partner, or somebody in the government side. But the idea here is that scale or large scale IoT is very, very hard. So having a large number of IoT sensors, pretend for a second you wanted to do that in this environment, would be quite challenging. And the infrastructure required to set that up would be also quite challenging. So the idea that Coliseum provides you the ability to modify or instantiate software radio stacks, modify the traffic patterns that it requires, and also inject different sensor streams, and allows you to mix and match all of those data streams is quite interesting. And again, this allows you to also apply AI techniques if you wanted for real-time wireless IoT emulations. So this question gets asked often. I'm sitting in an international audience room. Maybe a question comes, can I use this? What do I need to do it? Primarily, the good news is for academic supporters. So this is obviously, if you are a US researcher, it's free to use this. The entire cost right now is underwritten by grants and some charge models that we have for industry users. If you are international, we do, as long as you're an academic, we do right now support international use as well. So I'll show you how you can sort of request an account if you wish to play around with this, and we'd be happy to sort of approve you, onboard you. In terms of support, it's best effort. So again, more dedicated support right now, given that this resource is utilized very heavily, we are sort of skewing a little bit towards providing more support to the NSF researchers. And again, this is sort of just the form. Again, these slides should be made available. Primarily to request a team, if you're a student in the room and you want to play around, you'll need to go find an advisor. So we need somebody who is actually a faculty to request a team, and then he or she can add you into the team, and then you can sort of get started on using Coliseum. So, Coliseum is about 5 or close to 5 or 6 years old. So we have been sort of thinking about and have received some additional resources and funding to bring Coliseum into sort of, supporting beyond 5G and 6G kind of research. So today, Coliseum supports only a 1 kilometer by 1 kilometer physical area that can be emulated in Coliseum. What we are doing with the support of a National Science Foundation program, so NRDZ stands for National Radio Dynamic Zones. Yes. Sub-6. Right now it's sub 100 megahertz. No, you can program it, right? It's an SDR. So you can program, you can put the center frequency wherever you want, and then 100 megahertz channel around it. No, nothing is over the air. The point is this is not going over the air, right? This is just going over a coax cable. It's in a controlled environment. I'm not sending anything over the air. That question becomes relevant when you're talking about PAWR, or if you're talking about, the testbed that you have at Eurocom, then you have to be very careful on what you do. Here, it's pretty much the wild, wild west. So NRDZ is allowing us, so what we're doing is we're sacrificing the number of radio nodes that you can use. And again, it's simple math on how we had to make this happen. But we are now working towards enhancing that area that you can emulate in Coliseum to be 100 kilometers by 100 kilometers. And the reason that is because the National Radio Dynamic Zones is a program by the NSF to look at coexistence between satellite communication, terrestrial communication, passive users, Earth exploration satellites. And for that, you need large swaths of area to conduct and model interference studies. We're also moving in the millimeter wave direction. So we're going to build a version of Coliseum's channel emulation system that works at millimeter wave frequencies. So it'll be working all the way up to 28 and also to 60 gigahertz. So this is something that's again, supported by the National Science Foundation primarily. And, hopefully we'll be able to have a millimeter wave channel emulation system by the end of 2022. So I'll stop here. Again, happy to entertain, answer any questions. Hopefully, you sort of got an idea of what kind of experimentation research areas Coliseum and PAWR are able to enable for you. So thank you for your attention. Happy to take any questions. Thank you.
Okay, I see there are some questions and there are also some online questions.
A curiosity, the limitation on the size of the emulated area, 1 kilometer times 1 kilometer, is due to the computing power of the emulator. So why you are limited to 1 kilometer in the emulations? In the last slide, you have shown that for the existing Coliseum, you can emulate a scenarios that is 1 kilometer by side, no? Mm-hmm. Why there is this limitation of 1 kilometer?
Why is yeah. So this wasn't a limitation from the perspective of the hardware or software. This was primarily when so I should have sort of prefaced this early on. So Coliseum was an infrastructure that was built by DARPA for a very, very specific use, which was to showcase spectrum sharing in a small, congested and contested environment. So this was a requirement that they put. It was basically artificial in nature. But when we started to understand what we can do in terms of expanding the geographical area that can be modeled, and what this also does is it puts an enormous strain on the number of filter taps that we have to program so that we can pretend that we're in a large kind of a geographical area. So the idea was that people came to us and, they were like, hey, what do I do in just 1 kilometer if I want to do high mobility, want to have UAVs flying, want to model satellite communication? So that's why we sort of are moving into this particular direction. So yeah, so it wasn't a requirement or a design constraint. It was just how DARPA had set the system up, and now we're migrating away from it.
Any other questions in the room?
Yeah.
Like AMD, Xilinx, all that kind of stuff.
So right now we have primarily the NVIDIA GPUs. So in terms of acceleration in the path, so let me find where this main hardware one was. Okay, so right here, so you have your USRP X310 here. This again, it's just a Dell server. So if you wanted to, and we are trying to talk to AMD Xilinx, if we brought in a T1, T2, I just put it in here, and basically, we're actually working with a couple different vendors, Mellanox and others, where basically we can just put and right. And again, right now to outfit 128 of them with acceleration, that's just not feasible from a cost perspective. But if we wanted AMD to sort of support that experimentation, we'd absolutely just be able to plug that stuff in, and basically then it's just part of the experiment workflow. It's easy. So yeah, so it's hardware in the loop, which means you can bring other hardware easily and instantiate it here.
Yeah, I have also a question. You mentioned, you showed some results that on some XApps that were reproduced and repeated over different testbeds.
Yes.
Although the behavior was the same, there are some changes there in the achieved throughput and things like that. So why is that? And another question is, are these reproduced by the same team that actually developed it, or are they reproduced by another team?
Sorry, say that second part of the question, produced by other.
If they were reproduced from the same team across all the different testbeds, or
Oh yeah, yes. So the first one around the performance is that's the character. That's basically this, right? So you have some consistency in terms of what you were trying to achieve from a profile perspective, right? So here this was an experiment where you were sort of modifying how many resource blocks go to which slice. And in general, the trend outside of all of the noisiness and the throughput variations, because these test beds are different, right? One is emulation. So you see how beautiful, and constant it is. You move to an indoor over the air environment, you're seeing, who the hell knows what kind of noise, etc. You're seeing. It's a little bit more predictive on powder. And then, it gets a little bit more messy back again. So here, the idea was, what we wanted to demonstrate was, you have a heterogeneity of environments. The results are probably going to vary, but the profiles are still going to remain consistent. On the XApp one, it's the same team, right? So you developed the container and you just moved it from Coliseum over into the indoor test bed, then onto powder. And again, as I said yesterday as well, that you require some glue code, right? So there is some, and we have these toolkits. We have a way, if you want to, work with us and sort of move things from, Cosmos, for example, or Orbit or Nitos back into Coliseum. Very happy to sort of engage with you on that. I see there's a Q&A thing that popped up. Let me just see if that will be applicable. Oh, absolutely. Sorry, I was just, so the question here is around, if you can see it up there, is wouldn't spectrum sharing be applicable to non-US markets? Of course. I was just trying to give an example of why this is such a motivated topic in the US, because there is actual frameworks that the Federal Communications Commission has mandated, primarily the CBRS framework, and now the CV2X and 5G unlicensed in the 5.9 gigahertz space. So 160 megahertz that has been made available for Wi-Fi, but also 40 megahertz of that where CV2X applications need to be done. So there are a bunch of different studies that we're doing. But again, obviously, I want to acknowledge, there are other spectrum sharing frameworks. Now, the beauty here is that because we go DC to 6, because it's an SDR, whatever frequency you have either in Greece, in India, in China, and Korea, you're able to model that on Coliseum. So hopefully that answered your question.
Okay, so if there are no other questions, thank you, Manu, for your presentation.